Hello everyone. In this lecture, we're going to talk about directivity of aperture antenna. So let me write it here, directivity of aperture antennas. We've seen two important aperture antennas so far, and that's our open-ended waveguide antenna and a slot antenna. So we're going to talk about directivity of aperture antennas in this lecture, and then we're going to move on with our discussion regarding horn antenna. Now, let's see how we can find directivity of aperture antenna. That would be the same as finding directivity of any antennas. So let me write the steps. So you find E, and E will have two components. Remember that the propagation is along R hat. You are in the far field. So this is for the far field. Therefore, you're not going to have an ER. So after that, you can find average power density. You know that that's going to be in the R hat direction. And then you have your E theta square magnitude, E phi magnitude square. That's your average power density. And then you can find your radiation intensity, and that would be R2 times this portion, which I'm going to just write W without the vector sign. That's your radiation intensity. Then you can find the total power radiated, and total power radiated is essentially the integration of U over element of solid angle. And after that, you can have your directivity, which would be the radiation intensity of your antenna. Now I'm going to write theta and phi here, divided by the radiation intensity of an isotropic antenna, assuming that this is going to be radiated by that, which is P rad divided by 4, or you may write it as 4 pi U theta and phi divided by P rad. So this is the situation that we have for directivity. And if you are interested in maximum directivity, our notation was to use D naught. So because this is now going to be dependent on the angle. So D naught would be 4 pi U max or U naught divided by P rad. So when I'm saying directivity, I'm talking about this maximum directivity in this lecture. So this is the procedure that you can follow and find the directivity. But for aperture antenna, so I don't really need a new lecture to go over directivity. You already know that. But for aperture antenna, we have an easier way to estimate the directivity. There are approximations involved, but it gives us insight into what we can do to improve directivity and so on. So that would be my purpose here. So the way that this method that I want to explain works is that we're going to estimate the effective area of the aperture antenna, and it's not effective area in the sense of angle, it's the maximum effective area. So I'm just going to write AEM. So this would be the first step that we're going to do. After knowing maximum effective area, we estimate directivity as, so this is D naught, like that. So this is essentially the procedure that I'm going to find the maximum effective area, and I'm going to use that to find directivity. Remember, we've already used this equation in Friis equation. So we've essentially used gain is 4 pi lambda square, effective area or maximum effective area. That's what we used before. For aperture antenna, gain and directivity are usually very close because ECD, radiation efficiency, is very close to 1. So when I'm saying AEM and I'm plugging it here, and you see a difference between this relation, the reason is I'm assuming that radiation efficiency of aperture antennas are close to 1. So that's what we have. So that would be essentially our procedure. We're going to go from AEM to this directivity equation that we have over here. Now, let's see how we can find our effective area, maximum effective area of the aperture. So AEM is going to be equal to, so approximations are involved here. One of the important assumptions in this equation is that if this is your aperture, the direction of maximum radiation is perpendicular to the aperture. So this is one of the main things that's implicit here. So AEM would be equal to integral of ET, magnitude of ET squared ds. So this is over the aperture. So let me write it as S. S stands for area in this case, and A means aperture. So if this is the aperture, this is SA. This is the geometrical domain that you perform the integration. And then numerator is ET ds, and then you take the magnitude of the whole thing a square. So that's what we have for maximum effective area. So ET is the tangential field over the aperture of our antenna. For example, so let me remove this. For example, in the case of an open-ended waveguide antenna where we have X and Y, remember that this was the electric field over the aperture that we had. So this was my electric field. And as you see, the electric field is, of course, the one that matters is the tangential one to the aperture. So this is the subscript T. So if I have a field that is perpendicular, this is not in this equation. And for the fundamental mode of open-ended waveguide, remember, this is the only electric field that we have in the waveguide. It's going to be E in the Y direction. So automatically, this E is EY in the case of open-ended waveguide antenna. For the slot antenna, so this is the PEC plane, and then you get some distributions here similar to the waveguide. So this electric field is essentially the electric field that you will be using here. So now let's check that if it makes sense or not, at least in terms of dimension. Remember that you're going to get ET square, and eventually you're going to get ET square here. So the dimension of ET, volt per meter, will cancel, but here you're going to get ds, and then the whole thing is to the power of 2. So your ds is m2, m squared, meter squared, then to the power of 2, and then this is just meter square. So you end up with meter square, which is area, and the output of this is essentially effective area. So in terms of dimension, it makes sense. Now, this is the equation that I have, and I think perhaps the best way to understand this equation is to perform one example and perform calculation and find the effective area. For example, let's start by the use of this equation and, for example, calculate the effective area of an open-ended waveguide antenna. So let me start by writing electric field of this E is y hat E naught cos pi x divided by A. So we know that here is A divided by 2. Here is minus A divided by 2. Here is minus B divided by 2. Here is plus B divided by 2. So that's my electric field. So I'm going to start with that. So because the direction is y hat and is the same in both cases, I'm not going to consider it in the calculation. So I'm going to have AEM is going to be equal to, so this is going to be integration from minus A divided by 2 to plus A divided by 2 minus B divided by 2 to plus B divided by 2. ET is E naught cos pi x divided by A dx dy. This is going to be the whole thing to the power of 2. And then denominator would be something similar, but this time you're going to get magnitude of E squared. So you're going to get this. And then dx dy. So just the integrand would be squared in this case. And I'm putting magnitude around E naught because, I mean, this could be a phasor. And so I'm just going to say magnitude of E naught as simply saying E naught squared. So if I have that, now you see that my integration over y is, of course, from minus b divided by 2, b divided by 2, the same thing here. But the integrand in both cases does not depend on b, on y, so I can just take it out from integration. And also this e naught, I can also take that one out of integration because that also is a constant. So in the numerator, integration over y would be simply b. You take it out from that, but don't forget the square here, so you get b squared, and e naught squared would also, you can take that out of integration, and therefore you end up with just minus a divided by 2 to plus a divided by 2 cos square pi x a dx, sorry, just cos pi x a dx, the whole thing to the power of 2. And then for this one, you're going to get also your b, you're going to get your e naught square, and you're going to get minus a divided by 2 plus a divided by 2, this time cos 2 pi x a dx. So this is my integration, and e naught squared and e naught squared cancel. So you see, this is an important observation to see that this plays no role. So effective area conceptually means how good you are using your aperture. So if you look at, for example, this aperture, you see that you're not completely using your aperture because this part, for example, you haven't really used. That's the conceptual meaning of this. But now, that's the reason that this E naught doesn't matter. Is this the geometrical distribution that matters? And you clearly see that E naught is going to be, it has been canceled from numerator and denominator. So now let's continue with this and see if we can find the result. So now for this one here, I'm going to get b squared, and then this is going to be, the integral here would be a divided by pi sine pi x a, and this is going to be from a divided by 2 to minus a divided by 2. Then you need to square the whole thing. So that's what we have. So let me make sure that I did it correctly. Seems okay. And then I can just get rid of b squared. B squared divided by b would be just b. So I'm just going to keep 1b here. Divided by, now cos squared, to do the integration here, maybe I can do the following. Let me write it here. So cos squared pi x divided by a is going to be equal to 1 plus cos 2 pi x a divided by 2. That's what we're going to have. So let me check that if that's correct. That seems to be correct. So remember, I used essentially this equation that cos squared theta is 1 plus cos 2 theta divided by 2. So I used this identity. So if I do that, then if I integrate this, then the result of integration becomes 1 divided by 2x, 1 divided by 2x plus, I have a 1 divided by 2 here, and then a divided by 2 pi sine of 2 pi x divided by a, and the whole thing from minus a divided by 2 to plus a divided by 2. So that would be my calculation, which hopefully I haven't made mistakes here. So we're gonna know when we get to the final result. So now let me remove this, and continue the rest of the calculation there. And there I'm going to get AEM is going to be equal to B. Now, what would be the result here? If I substitute A divided by 2, I get sine of 90. So I get sine of 90 minus sine of 90. Sorry, sine of 90 minus sine of minus 90. That's going to be 2 here. So this part would be 2. So I'm going to get A divided by pi, and then 2, the whole thing, a square. And then I'm going to have 1 divided by 2. X would be A. So I'm going to get an A here, plus 1 divided by 2. A 2 pi. And if I substitute A divided by 2 here, I'm going to get sine of pi and sine of minus pi, which is 0. So this is going to be essentially 0. And therefore, I'm going to get B A square 4, and then I'm going to have pi 2, and I'm going to have A, and this 2 goes to the numerator, and that's going to be the situation that I'm going to have, which is going to be 8 divided by pi square, 8 divided by pi square AB. So that would be the final result. Now, let's just look at this final result for a second and see what's the meaning of this conceptually. So when you look at effective aperture, first you're going to realize that you have A times B. So if you look at this rectangular aperture that I had here, if I ask you what's the geometrical area of this aperture, you're going to immediately say, okay, this is a rectangle with one side A, the other side B. So the area is A times B. So this is supposed to also be area, but this is effective area. So, but it includes the geometrical area AB anyways. But then it's not 1 times AB, it's 8 divided by pi squared. If you approximate pi by 3, so you have 8 divided by 9, which is less than 1, of course. So your effective area is going to be less than the geometrical area. That means you haven't completely used your physical aperture. So that essentially means your effective aperture in the sense of antenna, from the perspective of antenna, is smaller than geometrical aperture based on this. And we talked about, for example, these parts that haven't been used. And now if we do 8 divided by pi square, we get approximately 0.81 times AB. So that's going to be 0.81 times AB. And if you look at that, that means effective aperture is about 81% of the geometrical aperture or physical aperture. So let me identify that by AP, which is the physical aperture. So now based on this, you may actually introduce aperture efficiency as well, which is going to be the ratio of AEM to AP, and you say it's 81% or 81%, 0.81. So this is a specific to this open-ended waveguide antenna. So now this is our effective aperture. So let's look at the whole procedure again. We had an equation for effective area, which was merely based on E on the aperture of the antenna. Now, we assume that we know the electric field on the aperture of the antenna. I had the expression here. This you can add a T here because Y hat is tangential to this rectangle, and E naught cos pi XA. So this was our electric field at the aperture. And now you substitute it here, and you started with calculation, and at the end you got effective aperture to be 81% of physical aperture. Now essentially you are done. and you can have an estimate for your directivity. So if I remove, for example, this part, so your directivity, or I should say maximum directivity, would be 4 pi lambda square, and then you're going to have maximum effective aperture. And that's going to be 4 pi lambda square, and then you're going to have 81% of AB. So that's our maximum effective area. Now, for an open-ended waveguide, if I want to get an approximate value for directivity, of course, I need to know my A and B. But before we discuss that, approximately at the center frequency of an open-ended waveguide, you can approximate this by 2 lambda by 3. You can approximate this by lambda by 3. So this is just an approximation here, but it's good to put these numbers to get an idea of the type of directivity that we can get. So if I have these numbers here, I'm going to get 4 pi lambda square, then I'm going to have 81%, then I'm going to have 2 lambda by 3, lambda by 3. And now as you see, I can cancel my lambda here, and that's going to give me 4 pi times 81% times divided by 9. So this is what I have. And now if I can get the number from my notes, I'll see that I'm gonna have about 2 point, this is gonna be 2.26, approximately 2.26. So that's the maximum directivity that I have. And if I convert it to dB, that's going to be 3.54 dB. 3.54 dB, that's going to be a directivity of this antenna. So you see that I have about 3.5 dB directivity in this case, which is not much, but in some applications are actually very much appropriate. For example, this type of antenna is a very common antenna in performing near field antenna measurements. So, and in those applications, although some directivity is good, you don't want too much directivity in those applications. So that's the directivity of 3.54. So you see, this procedure is very good in the sense that it gives you some insight about what's going to happen with effective aperture and so on. Now, with this insight that we have, maybe we can go for the maximum effective aperture. And if I ask you what would be the maximum effective aperture in this case, then you might say, okay, maybe we need to use the whole physical aperture here. And if we use the whole physical aperture, that essentially means you need to have an antenna, you need to have an aperture where electric field is uniform completely. Then you've used it completely. So if I have, for example, X here, I have Y here, this would be my A, this would be my B, and then based on this, you might be able to get 100%. But remember, if this part is metal, you cannot have a uniform distribution because you know that this electric field is going to be tangential to the metal and needs to go to zero. The same thing here. With the top metal, you have no problem because these electric fields are perpendicular to the metal. Look at this electric field is essentially perpendicular, but here they're tangential. So physically, you cannot have something like that. You may be able to do some tricks to, instead of having something like that, have like something that goes like this. So relatively would be more uniform, but complete uniform with metal here is not possible. So, but for the sake of discussion, we assume that, and sometimes in the exam, I will tell you that let's assume uniform distribution. Then that's just an assumption. But in some cases, you may not have a metal and you have very close to uniform, which is okay. Now, if you go by this again, so what would be electric field in this case? Would be y hat E naught. You see, I don't have any cosine or anything like that. It's just E naught. Therefore, my effective area would be equal to the integration over area, and this is just simply E naught for me, and ds to the power of 2, and then E naught square ds. Now, if we go by this, you see that E naught, you can take it out. So E naught square, that would be integral of ds square. And this E naught, you can take that out as well. And then that would be just the integral of ds. Now, integral of ds is a times b. But also note that E naught cancels. So the same discussion that we have, it's not dependent on the actual field. This is going to be AB square, area square. This is going to be just area AB. So you get exactly the physical area. So you see your effective area becomes exactly the effective area. Therefore, your aperture efficiency becomes uh, effective area, which is AB, divided by physical area, which is AB, which is 1. So you're going to get 100% aperture efficiency in this case, which is, and then if you go for directivity in this case, you can estimate maximum directivity by 4 pi lambda squared times effective area, which is simply AB. So that's a situation with this type of antenna. So you have a chance to increase your directivity. But just as a side note, don't think that necessarily having a cosine taper is bad. I mean, of course, the directivity of this type of field distribution is more than this based on the discussion that we had. This one is 81% of physical aperture. This one is 100% of the physical aperture. But that does not mean this is bad. Sometimes in antenna, you want to give a little bit of taper like that to the field distribution. And the reason for this giving this taper is to bring down the side lobes at the expense of directivity. So with this, you can bring down the side lobe level, but with this, the goal is to maximize the directivity. So that would be one example that one person might actually prefer this structure. So now, based on this discussion that we have, you see that if we want to increase the directivity, we have one we need to increase the aperture size, because if we don't increase the aperture size, for example, in the case of open-ended waveguide, we get to 3.54 dB. Now, what if I want to have more directivity, let's say 15 dB, 20 dB, and so on? And as you see, in all of them, the physical aperture plays a big role. For example, in this case is A times B. In the case of open-ended waveguide, it was the same thing, but then you had 81% of AB. So the size, which is A and B, is very important, and that leads us to the next discussion, which is for pyramidal horn antenna. So that would be our next discussion, and hopefully then you understand this much better by when we are finished with discussing the horn antenna. Okay, so we've seen that the role of aperture is very important in getting higher directivity. Now, we want to increase our directivity because we said, okay, with open-ended waveguide, this is the typical directivity that we have, 3.5 dB, and so we want to increase the directivity, and this is the way to go. This is essentially the reason that we have horn antenna. So now, if you, for example, look at this, which is the open-ended waveguide antenna that we saw in our measurement videos made by LabVolt, this is the aperture that you have for an open-ended waveguide. Now, this structure is a horn antenna, pyramidal horn antenna in particular, and as you see, it's a transition from waveguide to the horn antenna. So this waveguide that you see here, that we start from coaxial cable, then we go to the waveguide, and then we go to the horn itself. So as you see, this waveguide is the same thing as that. So you get to the aperture of the waveguide. So this is the aperture of the waveguide, and then the aperture flares out and forms a bigger aperture. Now, if you form a bigger aperture based on the equation that we saw earlier, we have a chance to get higher directivity. So compare this, which is the early part of this structure, and then flaring out, and that's essentially we can make our horn antenna. So this okay, so we learned that this horn antenna is a transition from waveguide. So think about so many things that we learned. For example, patch antenna will be evolving from microstrip transmission line. Now horn antenna is essentially evolving from a waveguide into a horn antenna. Now, to to start our discussion regarding horn antenna, let's classify horn antenna into three categories, and then we're gonna be focusing on one of them in this course. So this is, imagine this is your open-ended waveguide. So this is your open-ended waveguide, or sorry, this is just the waveguide. And then this is essentially the aperture of the waveguide, similar to this that we have here. So this is the waveguide that we have. Now the purpose is to flare out the aperture to make the horn structure. But then you have at least three options to do that. One option is, for example, you consider your H plane. So let me also have maybe some coordinate. It doesn't hurt to have some coordinate X and Y. And if you remember, this is the electric field distribution on the horn. So this is what we have. And based on this, you know that your E plane is YZ. So Y is the direction of electric field, Z is the propagation, and then H plane is XZ. Now, if you want to flare out the aperture, you have one of the options that you have is that you do expansion of the aperture only in the H plane. So H plane means along X essentially. So you're gonna get something like that perhaps. So you increase this size, which is along H plane, and then this you keep the same as before. So this doesn't change. So this is like that, and this is like that, and this is your new aperture. So the purpose is to go from this aperture to this aperture. But remember that the only thing you've done here is to increase this side of the aperture. So now if I make the connection here, so now look at this structure. If I do that, now I get a horn antenna, but this is a particular type of horn antenna, which is called H-plane sectoral horn antenna. And the way to remember this is that the expansion of the aperture occurs along X, which is essentially part of the H plane. Now, if you look at, for example, this antenna, and you want to see the main effect here is that, remember, the size of the aperture affects the directivity. Now, here, this is the size of the aperture. Let's call it a small a. Here, I have capital A, and this is your B, and the new size here, let's call it capital B, but this is going to be equal to B. But the capital A is going to be greater than A. So I'm going to go a small a and a small b for the waveguide, and capital A and capital B for the horn. So now, if you look at that, because this size is greater than this, then probably the half power beamwidths of this antenna, of the horn antenna in the H-plane, because remember, in the H-plane, the dimension of the horn is this capital A, is going to be, for the horn, is going to be a smaller than half power beamwidth of the waveguide, let's call it H-plane of the open-ended waveguide. So you see, because you are increasing the size in the H-plane, so the new antenna would be more directive in the H-plane. Subsequently, its half-power beamwidth becomes a smaller compared to that. So if you, for example, have a case that in the H-plane you want to decrease the half-power beamwidth, or you want to increase the directivity, you need to increase the size. And this is one way of doing that. And in this particular case, we're not changing the narrow wall of the waveguide. So H-plane sectoral horn, that would be one type. Now, to go with the next type, you can essentially guess what would be the next one. And in the next one, what's going to happen is that we're going to keep A as before. So capital A would be A. So our capital A doesn't change. It's going to be almost the same thing, but then we are increasing along this B dimension. So now I'm going to have a much bigger B, for example. So now this time my B is greater than the original B. And now if you create your antenna like that, this become your new antenna. And in this case, because the expansion happened along B, and along B is along Y, and YZ is E plane, this is called E plane sectoral horn antenna. And because the expansion is happening, the flaring out, the expansion is happening along the E plane, then you now have a bigger E plane compared to the original antenna, and therefore the half power beamwidth in the E plane of the horn antenna becomes a smaller than half power beamwidth of the E plane of open-ended waveguide antenna. So if you essentially want to tailor the half power beamwidth of the E plane, make it narrower, then perhaps you're going to go with E plane sectoral horn in this case. So that would be a second case for horn antenna. And then you naturally can understand the last category that we're going to see, and that would be expansion of the aperture in both directions. So you could perhaps increase your A. You could also increase your B like this. And now you can have a new antenna like this. So you see, this is going to be, this is in fact this one that we have here. So if you look at this and you look at it from this direction, so this is essentially a small b, and you see a small b increases to a capital B. So this is my capital B, which is greater than B. So now you're seeing this a small b and capital B. And if we look at from this side, this is my a small a, and now this is my capital A. So I'm going to get something like this. So this is going to be called pyramidal horn antenna. So this is going to be pyramidal horn antenna. And in this case, because you are increasing in both dimensions, it's expected that you're going to be more focused in both E-plane cut and H-plane cut, or half power beamwidth becomes smaller. In fact, in one of the labs, the video labs, I'm comparing the radiation pattern of open-ended waveguide antenna and the horn antenna, and you can clearly compare them. So this is going to make the half power beamwidth in both cuts smaller, and with this you also have other options. For example, maybe in some application you want half power beamwidths of E plane be similar to the half power beamwidth of H plane. So because usually, for example, with this type of antenna that one dimension is larger than the other one, you don't have similar half power beamwidths. But maybe with this now you have an option to keep the half power beamwidths in E plane and H plane similar for some applications. So that's essentially our introduction to pyramidal horn antenna. Now that we have this introduction, let's see how we should do this flaring out. And now to do that, let's have a cross section to study that. For example, if this is X, Y, and of course this is our Z, let's consider, for example, maybe X, Z plane. So I'm gonna consider X and Z plane. And then I'm gonna look from the top. This is my antenna like this. So this is from here to here is a small a. From here to here is capital A. This is essentially your top view. Now, the way that you flare out is essentially governed by this line and maybe this angle that you have here. So now, how you should flare out. I mean, what's the effect of this? Because you might say, okay, we've learned that directivity is 4 pi lambda square, and then I have AEM from before, but this AEM is related to aperture efficiency times physical area. For example, for open-ended waveguide, this was 81%. This was a small a times a small b. So you clearly see here that if you ignore this for a second, your maximum directivity relates to your physical aperture. So you might want to go very sharp out. But then the question is, I mean, if that's the case, why they chose this specific angle? Why they didn't go like that? Because they could have gone like this and have a very sharper transition. And with this length, you could have a bigger aperture. Go here and go here, and now you have a bigger aperture. Why that's not the case? So this is what we want to address here before getting to the design of horn antenna. So if you look at this open-ended waveguide or waveguide distribution in its fundamental mode, these electric fields in the waveguide, they are in phase with each other. So when they are in phase with each other, it helps you to get very good radiation perpendicular to the antenna. This is very also similar to dipole antenna, where you have these two in phase current. Now you have a set of in phase electric field. Now these are the electric fields, so they're essentially out of the whiteboard, and they are traveling together like this. Now when they arrive at this point, and then they continue their travel, if you for example assumes rays, for example, then the electric field that arrived here, then they're gonna eventually make it to this larger aperture. But look at the different options for distance. You could travel from here to here, you could travel from here to here, and so on. So you see that you have now different options for distance. So if you have a flare which is very extremely sharp like this, then look at the situation here that, for example, I need to replot that, but before getting to that discussion, you can appreciate based on this ray demonstration that when these are all in phase, but then when they arrive at this larger aperture, they're not going to be in phase anymore because they're going to be subject to different distances in terms of propagation. So when that's going to happen, you end up with an electric field here which are not completely in phase, such as open-ended waveguide antenna. But then although you're not going to be completely in phase here, but then you've gained an advantage that your aperture is larger. So of course, then there is a trade-off that how much you are ready to sacrifice this in phaseness for the bigger aperture. Now, if you make this horn like this, for example, then maybe that's not a good design anymore, because then you see, look at the situations here. This distance is from here to here, and now all of a sudden you have another distance from here which is completely different than this. And these differences, of course, with respect to wavelengths, but just I'm trying to explain it intuitively here. So the way that you flare out the aperture cannot be too aggressive, because if it becomes too aggressive, you get to extremely out of phase electric field here, which are not appropriate for getting good radiation. So you want to have a bigger aperture, that's understandable, so you flare out, but it needs to be smooth. If it's too fast, too sharp, too aggressive, then you get to a situation like this, and you can realize that, for example, this point, let's call it MN, and this MP here, then in terms of this distances, there's so much difference. So that gives us, that this idea is going to give us some guideline how this flaring out in terms of angle needs to be done, and that's going to be part of the design for the horn antenna. Okay, so at this point, I'm going to end this lecture, and then in the next lecture, we're going to go more into details of these, and I'm going to give you some equations for design, which is related to my discussion here, and then we're going to discuss how we can design a horn antenna. Thank you very much.